Now, in our previous section, we were talking about our rectangular coordinate system. So that's the whole X, Y, and Z thing. But sometimes we are moving along a curved path. It might be more convenient to write everything in terms of our normal and tangential coordinate system. Now you're like, okay, well, we've done this before. What's different? Well, let's talk about it. So the normal direction always points towards the path's center, and that's changing constantly. So, as we're going along a path, unless it's a circle, it's not going to have the same center at all times. Now the tangential direction is always, as it sounds, tangential to the path. Normal direction, normal to the path, tangential direction, tangent to the path. And then binormal direction is also normal to the path, but that doesn't ever show up. Now, since the equation of motion is a vector equation, we can take our three components and we can break them up and say, okay, well, our three equations are going to equal this. And here's the point where you say, wait a minute, where is the acceleration in the binormal direction? There isn't acceleration in the binormal direction. There never is. At least not for what we're doing. So here are some of the forces T and some of the forces N are going to be creating this. And if you're wondering about this one, it's still a third equation. It's just going to be equal to 0, always. And then from this, we will get two scalar equations, which are usually very helpful. That are some of the forces in the tangential direction will cause an acceleration in the tangential direction. Are some forces in the normal direction will cause an acceleration in the normal direction. And you're like, okay, but why is this helpful? So it's exactly the same, and it does. It does. But the one thing we said was going to be helpful is that one of these is always going to be equal to 0. However, there are other things we have to take into account. For example, the tangential acceleration, that one's easier to understand. It's simply the time rate of change of the magnitude of our velocity. And depending on the direction of our forces, it will either be increasing or decreasing. The normal acceleration, though, has multiple definitions. We can get it from our equations of motion. Some of the forces in the normal direction is equal to mass times acceleration in the normal direction. Or we can get it if we know the velocity and the rays of curvature of our path. This is extremely helpful. Do not forget this. Okay, don't forget that equation because you will need to use it a lot. Now, the normal acceleration, unlike the tangential, it doesn't change how fast it's moving. It changes its direction. It's always more or less trying to turn it towards the path's center of curvature. And so all of our forces will also be directed towards the center of the path or away from it in some cases. Now, if you have no idea what the rate of curvature is, if it's not given, you can calculate it using this equation right here. Write this down. Seriously, make sure you know where this is because it's going to come up at least once in a quiz or an assessment or something else that you're going to need to know this. And I would like for you to know where to find it. Now, it's in this one, 13.4 to 13.6 PowerPoint. Remember that. It's open notes, open book, so come back to this. Okay, so how do we solve these problems with the NT coordinates? Well, we do it when we move a particle that's moving along a known curved path. We first establish our NT coordinate system. We draw our free body and kinematic diagrams. And we have to remember that the normal acceleration is always acting inward. And the tangential acceleration can either be positive or negative. We apply our equations of motion in scalar form and we solve. Easy peasy. And sometimes it's going to be necessary to employ various kinematic relations. So, stop there for today, and the next time we'll jump straight into an example problem. So thanks for listening, and I'll see you all next time. Bye-bye.